Hello and welcome to another hands-on engineering video. In the last video, we saw how to wire up our GPS module and verify that we were receiving data. In this lab, we'll learn more about the kind of data that we were getting and how to write software to extract the data that we want. Make sure to check out the PDF for this lab, which is linked in the description below. We're assuming that your circuit is wired up from the last video for this code to run properly. Additionally, some of the code that we write today will use pointers. If you aren't already familiar with pointers, or you need a refresher, be sure to take a look at our video on them. The National Marine Electronics Association, or NMEA, has developed a standard for communication between various marine electronics, like GPS receivers. The strings you saw appearing on your screen from the last video were formatted according to this specification. For our purposes, we just want the $GPGGA strings because they contain latitude, longitude, altitude, and time information that's relevant for our weather balloon payload. All NMEA strings start with a $sign and end with a new line, or \n, and fields are separated by commas. Some other characters are also reserved by the specification, but this information is enough for us to begin parsing the positional data. Our code has three main goals: to retrieve the data from the GPS, to extract the GPGGA string, and to parse and store the desired information to the open log. The GPS module uses information it gets from satellites to generate packets that it continuously outputs. This kind of continuous output is called spewing. Since the data is just thrown at us by the GPS module, we need to be clever about how we try to find our GPGGA string. The way that we can do this is to use a buffer data structure, which in our case will just be a simple array and an integer pointing to where we are in the buffer. We'll refer to that integer as the buffer index. In our loop, we can spend some time filling up our buffer for later processing. Initially, our buffer will just be completely filled with null characters. A null character will denote the end of the filled portion of the buffer. When a byte of GPS data is read in, we'll fill the slot in our array that our buffer index points to and increment this index. As we saw in the last section, our data buffer correctly stores the incoming information sequentially. However, there's no guarantee about where the information we want is, or even if it's complete. The GPS could have just begun spewing out the GPGGA string, but the buffer filled up before we could store the whole thing. In this case, we've lost that data and will need to grab the next GPGGA string. This is why we need to process the buffer every so often and look for the string that we want, and a following \n. If we can find these two things, then we must have a complete GPGGA string in our buffer, and it's ready to be written to the output. We know that our GPGGA string starts with a $sign and ends at the first new line after that $sign. Once we have these two indices, we can simply use a for loop to go through our buffer, starting at the $sign and ending at the \n, and print every element between these two indices to our open log. The GPS code is nuanced and if improperly designed, will lead to headaches. To try and alleviate this, we provided you with a starter file. To successfully do this lab, you will need to complete a set of tasks described in the README. These tasks will ask you to implement code where the comments in the starter file direct you to. The starter file that we've provided has a .starter extension. Be sure to change this into an Arduino sketch by changing the extension to .ino so that you can open it in the Arduino IDE. In this portion of the video, we'll cover some ideas to help you complete these tasks. Besides for what a blank Arduino sketch contains, we have added a few helper methods that you will implement. In setup, we prepared the serial, GPS, and logger. The software serial library gives us an easy way to communicate with these UART devices. Do not alter the order of these statements. For reasons beyond what we're going to cover, Arduino serial does not play nicely with multiple peripherals on the same UART lines. In loop, again, we have some statements that force begin and end the GPS software serial. Do not remove or reorder these statements either. They are needed to ensure that the GPS and logger play nicely. This loop is meant to give the program some time to fill up the buffer. We make use of the millis function, which returns the number of milliseconds elapsed since the program started running. This number here, start time plus GPS data buffer size plus 2, is not something that you need to worry about too much. Just know that it is a number that represents how long we will spend per loop filling up our buffer. We chose this number to try to minimize how long the program spends filling up your buffer. In theory, we could have arbitrarily chosen a large enough time, say 2 seconds, or 2000 milliseconds. For this task, you'll need to define some global variables for your program. Like in the last video, you'll want to use a software serial object to manage communication with the sensor. Secondly, you are going to need a variable for your buffer index. Call it GPS data buffer index. Finally, you also need a constant to define the size of your buffer, which you should call GPS data buffer size. We've already provided you with the GPS data buffer implemented as a character array. We explicitly initialize every element to 0x00, or null. This isn't strictly necessary for global variables, but we recommend you always make sure that your variables, especially array values, are initialized before you use them. This is because local variables, for instance variables defined inside of a function, will have garbage values by default, and using these values will lead to nasty undefined behavior. As mentioned, we denote unfilled slots in our character array as the null character, \0. In order to reset your buffer, iterate through every slot and set it to this null character. Additionally, you have invalidated your buffer at this point, so your index no longer makes sense. You should set it back to 0 so that new data gets put right at the start. As an optimization technique, consider whether you really need to fill every single character in the buffer to be null. What if the character you're looking at is already null? For example, if the reset was called when the buffer was only partially filled. Do you really need to set anything past that null character to null? Consider this when you're writing your loop. Three functions are left incomplete for you: pointer to first GPGGA, distance to first GPGGA, and distance to first new line after GPGGA. Follow the RME documentation to implement these functions. For the first of these functions, pointer to first GPGGA, use the C helper function strstr. Here's the man page for this function. This function can take in two parameters: the string that we are searching for, called a haystack, and the substring that we are searching for, called a needle. Recall that a C string is just an array of characters, and the end of the string is denoted by the null character, \0. Which variable in our program could be treated as a C string resembling the haystack? Additionally, what substring, or needle, is our function supposed to look for? Consider this when you're implementing the function. For our last function, given a pointer to the $sign of a GPGGA string, get the distance from this pointer to the beginning of the array as an integer. If the pointer passed in is null, then return -1. How can we do this? Well, first let's investigate arrays for a second. A pointer can point to any block in memory, including any of these slots in the array. If our pointer to GPGGA function returns a pointer to, say, the third element, then it turns out that we can just subtract the pointers to get how many blocks of memory are in between these two pointers. So, if we take a pointer at the slot index 3 and subtract it from a pointer at slot 0, we'll get 3 as our answer. How do we get a pointer to slot 0? Well, we could write something like this, ampersand GPS data buffer at index 0, or we could just say GPS data buffer. The reason that we can refer to the array by name and get a pointer is that under the hood, arrays really are just a pointer to the first index in memory of that array. When you try to access the nth element of the array, the program actually goes to the first element of the array, goes forward n elements, and then dereferences the pointer. What this means is that this syntax, ampersand GPS data buffer square bracket 0, is actually semantically the same as this syntax, which reads the address of the value that dereferencing the GPS data buffer pointer at an offset of 0 yields. So, to complete this task, get the number of slots between the pointer passed into the function and the first slot of the GPS data buffer. For your last function, distance to first new line after GPGGA, given a pointer to the $sign of the GPGGA string, find the distance from the beginning of the buffer to the first new line after the GPGGA string. If the pointer passed in is null, or there is no new line found after the $sign, just return -1. In order to accomplish this, you'll need to combine what you learned in implementing the first two functions. Similar to strstr, there is a function strchr, which takes in a string s and a character c. Use this function by treating the GPGGA pointer as a string, and the \n or the new line as the character that you're searching for. Once you get this pointer, get the number of slots between it and the first slot of the GPS data buffer. For your final task, we're going to complete the loop. As mentioned when we were going over the general starter file code structure, this while loop is meant to give the program dedicated time to fill up the buffer. Additionally, we mentioned that the millis function returns the time in milliseconds since the Arduino program started. If we wanted to write a while loop that ran for 3 seconds, how would we accomplish this with millis? If you're still confused, consider that we can store the value of millis into a variable before our loop begins, and then, in the loop conditional, we can compare the current time to our stored time. When we are setting a slot in the buffer equal to data from the GPS, how do we read from the GPS? As a hint, take a look at the last video, where we were just printing this data to the console. Finally, iterate through the buffer using the two distances you found, and write out only that portion of the buffer to your logger. That's all we have for you today. Hopefully, you learned something about NMEA strings and how to handle spewing data with a buffer. We hope you enjoyed the video. Please leave a comment below if you have any questions, and we'll try to get back to you.